Okay, so for an application, we can look for an application of adiabatic compressions, we can look at a diesel engine. So a diesel engine is one where there's a cylinder, and the cylinder is a piston, and the piston moves down and compresses the gas, and it gets it so hot that it ignites without needing a spark plug. So it must get pretty hot. So let's figure out how hot. And the compression ratio, that is how much the gas, the fuel-air mixture is compressed, is a factor of 20. So at the end of a compression, we have 1/20th as much volume as when we started. Okay? And we also need some data. We need to know that CV for air, of course, it's a weighted average of nitrogen and a little bit of oxygen, and it comes up to about 20.8 joules per mole per Kelvin. So those are our givens. All right. Well, from the work we did earlier, we saw that if we have a reversible adiabatic compression of an ideal gas, we have an expression that relates the change in volume to the change in temperature. Now we should be careful here. This is for reversible adiabatic expansion of an ideal gas. Well, okay, air pretty close to being an ideal gas. Isn't that pressure is not too high inside the cylinder of the car. It's adiabatic, yes, that makes sense because it's such a fast compression. We compress this so fast there's no heat transfer. Is it reversible? Well, no. If it's fast, it's not reversible. So this is only an approximation because it's not truly reversible. And so that means that this is going to be an approximation. And so we should have that as a caveat when we do this problem, that the answer we get is only an approximation. Okay. And we saw earlier that we can adapt this expression and say this is V1 over V2 to the R over CV. Okay, great. That's more heat capacity. So if we assume that the air intake to the car, that the temperature of the fuel-air mixture, T1, is going to be just 300 kelvins, just a tiny bit warmer than room temperature, then we can ask what T2 is. So let's go ahead and solve for T2. We see T2 is equal to T1 times that ratio, V1 over V2, to the R over CV. And if we plug in numbers, say T2 is equal to 300 kelvins, and V1 over V2 is actual 20. Right? We start off with 20 times more volume than we end up with when we compress those gases. And then R, we have 8.314 joules per mole Kelvin divided by CV, which was 20.8 joules per mole Kelvin. And notice that the units do cancel, and they have to, because that's always, we can't actually have units in an exponent. And when we do the math, we get 993 kelvins. Okay, or if we convert this, that is around 720 degrees C. And that's quite hot, and it's plenty hot enough to ignite the fuel-air mixture, which is why diesel engines do not need spark plugs.